Alright, it's chain rule time, and this is without a doubt the most important section that we learn related to derivatives. So I'm going to show you a couple of things here really quick. So if you look at these functions here, the point here, we have all the rules necessary to differentiate these functions. They're fairly basic. You can think of things like the power rule, the trig rule, and also the quotient rule. So the chain rule is going to allow us to differentiate functions that are similar to these, but you can tell by glancing at them that they're more complex in their structure. So when you look at something like this, there's definitely a similarity, but we would classify this as a power function, something raised to a power. This is a slight variation on cosine, and here we have the square root. So if you were to just talk about this first one, this being cubed, we would treat this as a power function, but this is not x cubed, it is x to the fourth plus 3 raised to the third power. So what the chain rule allows you to do is to really deal with composite functions. So you might recall a composition of functions in your algebra class. So when you have functions inside of functions, the chain rule will handle those functions very well. So this lesson is really all about not how do we differentiate these, because we already know how to do that, but how do you find the derivative of functions that look like this. Alright, so basically I'm going to start out a little bit on the development here, what we're going to do. So we'll start with that statement there. Okay, and again, so this is the basic setting that we're going to work with. It's a composite function because you can see there's a g function inside of the f function. And the moral of this entire lesson is going to be, how do you find the derivative of a function that is set up in this manner? So what we're going to do here is to break this function down into pieces. And so the first thing we're going to do is to identify the inner part, the function g, and we're going to give that a name. So u is equal to g of x, right? So we're identifying that. And then we're going to go back to the original statement and just rewrite it with this inside function. So we're going to take this statement here and just write y equals, right? And we're going to put u in place of g. So I know this kind of looks like a mathematical curse, but all we're doing is just letting u equal g of x. So probably the most important thing here is to realize that these two statements, I'm going to put an asterisk on each of them. Okay, these two statements together are exactly the same as the statement that we started off with, right? So all we're doing is we're introducing one variable here and just breaking this function into parts. Okay, once we understand that, then the chain rule is actually fairly simple. So I'll write it down here, dy dx, right? How you find the derivative. So dy dx here is given by dy du. And then we multiply it by another derivative, and that is du dx. Okay, so when we look at this, dy du is referring to this statement y equals f evaluated at u. So this is the derivative of the outside function. So this is really the outer part, right, that we're finding the derivative of. And then du dx is referring to this top statement here. So g is the inside function. So this is the inner one. So if you want to describe the chain rule in words, we take the composite function, we break it into two pieces, and then we find two derivatives, right? The derivative of the outer function, but we keep the inner function intact, and then you multiply that by the inner function. And so the chain rule simply subdivides your function into components, and then you find the derivatives of those components and multiply. Alright, so there are a couple of different ways that you can express this. This is the most natural way here. So I'll just put this up here so we can see it. So dy dx equals dy du times du dx. And some people prefer a different way of expressing this. The important thing to understand is it's the same thing. So if you look back at f of g of x, the derivative dy dx, or y prime, is f prime evaluated at g of x. So you could tell this is the derivative of the outer function, but the inner function is intact. And then you multiply by the derivative of the inner part. So you can see you're multiplying by g prime. So that is basically it. This is what the chain rule looks like. This is sort of abstract because we have this abstract general setting here. But you keep this in mind and you go through a couple of examples and it starts to make sense. Right, so I think just for the sake of helping us out, I'm going to leave this up here so that way we can look at it. And we're going to spend some time going through just a couple of examples. Okay, so I'm going to go through this one first. Okay, so when you look at something like this, what we want to do is, let's see if we can use the chain rule. So you want to identify the inner part of the function, and you can see that's this part here that you're squaring. So u is equal to x cubed plus 3. Right? That's our inside part. And then we're going to attempt to rewrite this y equals u squared. Right? So we're going to use this information here. And again, the big thing is just to understand that if you have these two statements together, it's exactly the same as that. Right? So you just have to think about that. Okay? And then the chain rule is right here. We can see it. So dy dx is equal to dy du, and then times du dx. Okay, and dy du is this bottom one here. So when we differentiate this, we get 2u to the first power. Right? We learned that a while ago. And then du dx is this top relationship. So the derivative here is 3x squared. And that is pretty much it, right, for a problem like this. What we would want to do is to give the answer back in terms of x, because that's the way it was given to us. So what we have here is 2u. So I'm going to rewrite this here. And then we have this here. And then what you might want to do is a little bit of the simplification, and then I think that would pretty much be your answer. So I'll bring this up here. So we have 6x squared and x cubed plus 3. Right? And that's how it works. So you back up and look at an example like this, and it all comes from just finding these two derivatives, right? And that really happens in the first line right here. And then the rest of it is pretty much algebra. Okay, so I should definitely mention that there are other ways to do this problem, and you guys can probably detect that. So let's take a quick second just to talk about Plan B. Okay, in fact, I think option B is even easier. So if you look at this problem, one advantage you have here is you could just multiply this out, because this power is really small. So you could do x cubed plus 3 times x cubed plus 3. So if we do that, it looks like this, right? So x to the 6th plus 6x cubed plus a 9. And then notice here it's very, very quick to find y prime. So you would get 6x to the 5th plus 18x squared. Okay, and if you look really carefully, or not so carefully, it should be the same, right? So you look at what we had from the chain rule, and everything looks good. So this, without a doubt, is an easier way to do the problem. But notice if this power is slightly higher, then you would want to go with the chain rule path, right? Because that's a much simpler way to get the answer. All right, so let's switch out problems here. So we'll do one more. Try something different. So on a problem like this, I don't think it's as obvious, right, a simpler way to go about doing it. So we're going to try the chain rule here, and we're going to identify the inside part, right, which is this part under the root. So we identify that. and then rewrite your function, y equals the square root of u. Okay? So again, always look and make sure these two statements, when they're blended together, give you exactly this. Okay, and then we go right into the chain rule. So we have two derivatives that we want to find, dy du, and then also du dx. So dy du is this one here. So you might want to think of this as u to the power of 1/2, right? And so when you differentiate this, we have 1/2 u to the negative 1/2. And that's just the power rule. And then du dx, we would differentiate this top function here. So parentheses are important here. So this would be 8x minus cosine of x. And so at this point, the calculus work is pretty much done. We're going to take this top function and put it back in place here, and then just rewrite the problem. So I'll get rid of this. Okay, and we'll rewrite this. So if we continue the process here, y prime, this is going to look like 1 divided by 2 root u, and we're still going to have this chasing it, like that. And then the u in the problem was the inside part. Okay, so I'm going to combine two steps here. So this is going to be 2 times the square root, and we're going to rewrite this. Okay, and then you can bring this upstairs. So 8x minus the cosine of x. So this is a more complex looking expression, right? But given this function here, the derivative dy dx or y prime, it's right here. So you can see you have to use the power rule with u to the 1/2, and then you also have to use the rules to differentiate the inside. Okay. Okay, so there's basically just one more thing I want to develop here. And you can accuse me of calling this really bringing up an academic example, because this is kind of a weird function, how we would differentiate it. But this illustrates a point very, very nicely, and that's the thing I want to talk about. So if you had something raised to a really high power here, we would definitely want to identify this as u. So u is equal to x squared plus 1, right? And then rewrite this with the u. So y is equal to u raised to the 50th power. So if you use these two statements together, then the chain rule, right, using this is going to be pretty smooth. So this one here I have worked out. We could just take a quick look at it, right? And we can see what's happening here. So we have dy du times du dx. So when we differentiate this piece, it's going to give you 50u, and then you drop the power, and then you have to differentiate the inside part, and so we get 2x out of that. So the key here is everything happens right here, right? All the calculus, and then you put your x's back in, and then you might want to do some multiplication, and you get your answer that shows up right there. So this is a good example to illustrate a more general power rule that we have in calculus. So this one here I want to show you guys so you can see it. So this is the general power rule here. So this is saying if we have a power function, right, some inside function raised to a power, then the way that we differentiate the function is the power goes out in front, you keep the inner function, you drop the power by 1, and then you have to chase that with looking at the inside and then differentiating that. So what you might want to do is to compare this with the old power rule. This is the one we know very, very well, right? So you can see that this chain rule version is a variation of this, right? It has a very, very similar structure to it, right? Power out in front and then drop the power by 1. So the main thing here is this differentiates the inner part, And so you can rewind the clock and think about what that means, right, for an earlier section. Because in the old power rule, the inside function is actually just an x. So if you wanted to apply the chain rule to something like this, you could multiply by 1, but you could tell that we never bothered to write that down. Okay? So the big thing to take from this is to notice that if you understand how the structure of the chain rule works, then it really turns out that you don't have to do any of this identification, right? Let u equal something. Because if you look at this line, the result of the general power rule, you can see it third line down, right? So it's right here, put a star. Okay, so using the old chain rule that we just talked about, you can see that if you have x squared plus 1 to the 50th, you can see it right here, this is 50, and then you keep the inner function intact and you drop the power by 1, right? And then you look at the inside part and you differentiate that. So this is really late in the process of using the chain rule, but notice that if you understand the general power rule, this is instantaneous, this result is immediate. And then all you'd have to do is to multiply these, and you have your answer.